الآن ننتقل إلى الدكتور أحمد الناوي، المؤسس والرئيس التنفيذي لجامعة التعلم الافتراضي. طبعا دكتور أحمد شغل منصب أستاذ الفيزياء في جامعة محمد الخامس بالمغرب، وانتقل إلى ألمانيا، وانتقال لإجراء البحوث التأهيلية في معهد هان مايتس في برلين ألمانيا، ويشغل منصب رئيس مجموعة الأبحاث في هلموتس زيندروم ببرلين للمواد والطاقة، وكمدير أبحاث لمجموعة الطاقات الشمسية في معهد أبحاث البيئة والطاقة. وفي الوقت نفسه يعمل كأستاذ مشارك، عمل كأستاذ مشارك في جامعة حمد بالخليفة، ونشر أكثر من 300 مساهمة علمية، بما في ذلك 200 ورقة بحثية تمت مراجعتها من قبل الزملاء، والعديد من الكلمات الأساسية التي ألقيت في المؤتمرات. تم تصنيفها من قبل جامعة ستانفورد كواحدة من 2.2% من الباحثين في العالم، من بين 224,856 باحثاً في الفيزياء التطبيقية، مرتبة من قبل الجامعة الأمريكية المرموقة. طبعاً الدكتور أحمد هو عضو دائم في هيئة تحرير مواد الطاقة الشمسية والخلايا الشمسية، وعضو بارز في IEEE. خلال مسيرته المهنية أشرف على أكثر من 40 أطروحة مكتملة، وعمل مع 15 طالباً في مرحلة ما بعد الدكتوراه في مجموعته. يشغل حالياً منصب رئيس المجلس العلمي لأريزون، ومنخرطاً بعمق في إنشاء آليات الدعم وتعزيز البحث والتطوير في مجال الطاقة المتجددة وتقييم ومراقبة مشاريع أريزون. بروف أحمد، أهلا وسهلا بك، تفضل.
شكرا أستاذ صالح على هذا التقديم. أشكركم جميعا. سأتحدث بالإنجليزي أو فرنسي أو ألماني كما ترون، لكن سأتحدث بالإنجليزي علشان الكونسبت بتاع الجامعة الافتراضي هو عربي إنجليزي، ثم إذا كانت مشاكل حيكون فرنسي ولغات أخرى إن شاء الله. سأتحدث عن هذه الجامعة و I will switch to English. So we are our objective in this virtual learning university is connecting with students in online courses, and students from Morocco, from Africa, from Arab world, from everywhere at the end of the day. And I want to give you our philosophy, our concept. Again, because I have already talked yesterday, but the technique was not working very well in Casablanca. So today, thank you God, it's working. So of course, my course will start today just as an introduction about our university, but everyone who wants to get in touch with us, there is here an email address to write to me, or I think this email, Ustad Salim will see it also, and he can be enrolled in our course. But let's start now with some very important issue, which is the baseline of our virtual university, our course. As you see here, the global warming and the carbon footprint. I just show here a schematic where we are already above 50 billion tons of carbon oxide in the atmosphere. I wrote here some word about how to calculate. For chemists, they know exactly these numbers, but for other maybe it's not necessary. There are now software to do this. But if we look to this schematic here, we can say that we have already a lot of carbon dioxide in the atmosphere, which is responsible of this global warming. And the objective is not to go further with this global warming, these 2 degrees here. So we have to stop technologies that run on fossil fuel. تقنيات تعمل بالوقود الأفوي. That's the solution. But how to do this? If we go in this direction as business as usual, استمرار في نفس المسار, to produce carbon dioxide in the atmosphere, that it will be a catastrophe. And that's what we are doing. If we stay, that is a diagram of maybe few years. Now we have maybe a little bit more than 4% renewable energy, الطاقات المتجددة, but we're still very poor. We don't use too much. We use more oil, more carbon-based technologies. So we have to find other way. One of them is to hold the current emissions. It says, okay, we have now too much carbon dioxide in the atmosphere, then let's stop and start seriously with renewable energy, with the green industry, and see if the nature will absorb this carbon dioxide in the atmosphere, and we will have a safe planet, because we don't have another planet. There is no planet B. But the most intelligent and better way is to really use and reuse this carbon dioxide in the atmosphere. So this means we have really to find technologies that run on green fuel, تقنيات تعمل بالوقود الأخضر. And we can remove the carbon dioxide in the atmosphere, we can recycle it, we can reuse it, etc. And we try to get rid of this carbon-based industry. As you know, there are measures on the industry emission, which coming. So in the future, in the next future, we will mark carbon footprint on product, on tomatoes, or vegetable, etc. What you sell to the oxygen. هناك وضع علامات مقدار البصمة الكربونية للمنتوجات. This will happen. So we need to decarbonize our companies for global export. Morocco export to Europe, or the export to Europe, is estimated to around 70%. And in few years, Europe will just tell us, we don't want to have your export because it's done using carbon-based industry, for example, and then we have problem. So the export to Europe will be subjected to carbon taxes. الصادرات المغربية إلى أوروبا يمكن تقديرها بحوالي 70%. التصدير إلى أوروبا سوف يخضع لضرائب الكربون في المستقبل. Okay, that's just an introduction about this global warming. Now, how we are working in the virtual learning university. We have professors, top professor, and they create syllabi based on industry need. That's how we work. And this is, for example, this table here called the Mendeleev table of the element, الجدول الدوري للعناصر الكيميائية. And we try to see what are the needs of the country, of our country, for example, and to construct our syllabus or our syllabi based on this need, but not only. So we work with Professor Ben Youssef. He's expert in what we call the simulation and modeling, التقييم من خلال المحاكة والنمذجة. And he's working on very important subject to predict the material for the future. And he just gave his talk about two-dimensional materials to use it for hydrogen, green hydrogen production, for solar cells, for the storage of hydrogen, etc., etc. So this is very important. That's what we call it knowledge development. So through physics, mathematics, computer science, etc., the student learn a lot of physics, a lot of phenomena, a lot of process. Then we have to go in the direction of the economy. You can make a concept of material, new material, for example, but if it's too much expensive, it will not be public. The public will not accept this kind of material because it's too expensive. So we have to narrow. You have to use methods which narrow your choose based on economic and the process, how complicated the process, what you want to use to make this industry. Then you have to identify suitable material. You want one material for sensors. You want one material for solar cell. You want one material for medicine. You want material for this, for that. Then we have, and here you split the student according to their interests. Some are interested in solar cells, some are interested on medicine, etc., etc. Then we have, once we have made this exercise, we have to see the mechanism of failure, the stability of this material or this device. You don't want one material or one device for 24 hours. You want it for 24 years. For example, solar cell or solar module has to work for 24 years in order to get your money back. Maybe you get your money back in few years, but then you gain afterward. Then, and that's what we call research and development, these two items here. Then, if you do research at the university and you demonstrate that something is working very good in the laboratory scale, then you have to make your proof of concept and to go to negotiate with the industry in the level, in the technology readiness level of from 6 to 9 in order to build up the industry. So in this exercise, we go from atom, knowledge development, to, for example, devices by developing the technology and the business if you are talking to the industry and to the bank also. Okay. So in this exercise, it's very important to have objectives. That's the point. And for every objective, you have to build up the syllabus and the way how you will teach, etc., etc. To be with us in this university, you have just to go to the link, and then to enjoy. We have videos, we have syllabus written in English, and you can learn a lot. And then you decide that you want to be in this course or that course. Everything is without money. You don't pay for that. Okay. This is, for example, Professor Binus have already given his talk today, and that's one of his working on subject where he worked during 40 years, 40 years, and therefore you cannot find better professor if you enrolled in his course. So he will develop with his team different methods from ab initio, from you see here the scale, the length scale, from angstrom to continuum. And depending of the requirements of the student, he will develop 1 or 2 or 3 of these methods. And you can see in his, if you go to the web page, you can see his video from the last conference. We will also make the video from today. Ustad Salim, he will do this. So you can see also principal investigator. He has a team to bring people from the theory to the practice, and you can register if you are interested in this course. Okay. There are others. Myself, I have also a course on PV technology, And there are also courses to how to learn what we call the social entrepreneurship. That is very important in our Arab world to be entrepreneur, but social one, very generous one. And also there are courses about this. Okay. There are also courses on batteries. We have colleague, Professor Saadoun from University Qadi Iyad. He helped us with, he's very good in lithium batteries, and he has a very good syllabus. And you can also go to see his video to register in his, to read his syllabus and to register if you are interested. So let's talk a little bit about photovoltaics. Well, I will develop a huge course, but just to give you an idea about photovoltaic. In reality, photovoltaic is very easy to understand. You have the sun, the solar spectrum, what I show you here. And you have to find a way to convert all this energy, that's a lot of energy, into a power, electrical power. Electrical power is always electrical current and electrical voltage. And if you divide the product of the current by the voltage, and you divide by this energy with every day, God bless us with, the 1,000 watt per square meter, you will find what we call the power at maximum power point here, at this point. And that's what you can use in your home for warming your home, for electricity, etc. All the physics behind this will be studied in my work, in my course. Of course, we try to go as ideal as possible how a solar cell has to be in order to get the maximum of this efficiency here, what we call in our jargon, Shockley-Kaiser limit. But this you will learn what's mean this. So all this is knowledge development, what you get from this course. So, of course, I say this is very simple, the photovoltaic, but it's not easy technologically. If you have a spectrum, and Ben Yusuf talked about this also before, you can find one material which absorbs part of this spectrum, another material which absorbs the other part. And we have to find a way to mix material in order to have the whole spectrum, what we call tandem solar cell. We will also study the first technology which is in the market since long time, and which the silicon wafer technology, and we will study how this is working, etc. Every detail will be in my course, and how the mechanism, how the electron, how the light is absorbed, how the electron and hole are separated, and how we generate the current, we generate the voltage, how we calculate the current using the mathematics. Mathematics is very important, but we don't do pure mathematics. We use mathematics only for need. Okay. So another problem, what I'm very much interested is the photovoltaic module for the desert, for the harsh environment, for the hot climate. And this is very important, what we don't find very much in everywhere. And we will study this kind of relationship where you will see how it's very easy to establish in order to know how your voltage or the current or even the power, the product of the voltage by the current, how it's changed when your module get hot. And this is very important. And there are all these stuff are in the way that one day you can, if you take the data sheet, the technical sheet of the constructor, what you will get from the constructor, you will understand exactly what he will give you. So all this stuff will be studied very, very carefully. A module you imagine your car, you lit your car in the summer somewhere. When you come back, you cannot get inside because it's very hot. It's exactly the same for the module. The module is there are glass, there are a lot of things there with different thermal calorific properties. And therefore, some material get very hot, some material get a little bit hot, etc. And all this will give you a problem that the power will get down. Okay. Here is the characteristic, for example, what I showed you before, but here for different temperatures. You see for 0 degree Celsius, you have this characteristic here, but at 75 degrees, you lose a lot of voltage. And if you lose a lot of voltage, you will lose in your power. So we will study every item of the module, and we know why we use the glass, why we need the encapsulant like ethyl vinyl acetate, for example, a polymer, etc., etc., and also how to change this encapsulant. If there are some new encapsulant, we will learn this. Okay. We will also study when you have your technology. For example, that's the technology of silicon. Actually, we will study how you, if you want to do some modeling, macroscopic modeling, how to translate this technology here, which is in real time, to electrical circuit, and you can understand exactly what you are, why your power is dropping, etc. So all this stuff you will learn in this course. Okay. We will also go further. We will not stay only with silicon. We will go to another materials. And always we go from the Mendeleev table. Silicon is a very nice material, very easy to dope, N-type and P-type. It's just to take silicium. If you substitute one silicon with phosphor, which is in the column 6, in the column 5, sorry, then you will gain 1 electron. If you substitute one silicon with gallium, or normally the industry use bore with 3 electrons, then you will have now electron, 1 now electron, what we call hole. And then you can have your p-n junctions. We will discuss all this. Then we will go to binary compound, gallium arsenic, cadmium telluride, etc., where you can also get it from Mendeleev table. And we will see what's happened when you go from silicon to binary compound. I will explain to you that there are 2 kinds of culture here. There are people that will stay working with this material here, what we call 2,6 compound. And this is material, you cannot dope it. They are naturally doped. They are either N-type or P-type. But there is another culture. If you have a lot of money, you can study material where it's behave like silicon. You can also dope it N-type and P-type, but you can control the doping like silicon. And you can go further to ternary compound. And we will explain to you that the physics of silicon will stay there, but we have to take we have to be very careful. And so this kind of the physics has to be smooth, and he has to have a kind of innovation and reflex to understand thing, and you will understand that you will always have this behavior that one atom is surrounded with 4 atoms, but it's not exactly like this, and he has to find the right theory to explain stuff. So we will study silicon to zinc blende structure, to chalcopyrite, copper, indium, gallium sulfide, selenite, to casterite, etc. All these new material. The first one is the first generation, and these two here are the second generation of thin films. Okay. Then once you understand the knowledge, you get the knowledge, you will learn about the technology. So for example, here, that's the 10 film technology where I worked for more than 25 years, what we call monolithic integration. This is substrate glass, for example. This is molybdenum. And this technology, I worked a lot with. You can, for example, use a laser, pulsed laser, to cut your molybdenum. Why? Because you want your customer want a module with let's say 100 volt or more than 100 volt. He will tell you what he wants, and then by laser you can already predict technologically, not theory, how much voltage you can get at the end of the day. And that's how we do it. We cut with laser, a pulsed laser, then we deposit a material. That's the material here is if you give me some time to write the material here, it's a material with copper, indium, and gallium. You put it together by, for example, evaporation or sputtering, and then you make it in we call rapid thermal processing. That's just 5 minutes in the 550 degrees in atmosphere where you have sulfur and selenium, and then after some few minutes you have your absorber like this here, the one here you see in this figure here, and then you continue some patterning P2, and then you have to deposit one material like cadmium sulfide or zinc sulfide, and then again you have to deposit the zinc oxide, for example, and then at the end you will have sorry, I have some animation, and okay, now it will work, I guess. So in this system, with this monolithic integration technology, you will have the first cell or the bottom or the back contact of the first cell is connected to the front contact to the second one, etc., etc. That's why we call it series monolithic integration. And this, when you see the module in the commerce available commercially, you will see just this. But behind this, there is a lot of technology with laser, with a lot of different layers here. So this kind of module here is already the readiness level of 9, where it's already commercially available now. Okay. So now a little bit more detail about my course. We have a part 1 when I will study with the student the solar radiation, very, very, very in detail. Then the physics of solar cell and silicon wafer, then silicon wafer manufacturing, like what I showed you just now. Then the 10 film technology, etc. So we have a lot of different chapters to be done. But the objective, once you know all this details, the knowledge development, you will learn what we call the balance of system. So how to use this module to power supply your house, for example. And you cannot connect your module directly. You have to use some, what we call the inverter. I wrote it here in French. The regulator, if you want to have some, if you want to regulate batteries to work during the night, etc. So all this balance of system will be done in this course at the end. So you will learn how to do this by yourself. So we will go from atoms until the system here. Okay. So, of course, for every chapter, you have a number of hours. So we did this, that is the American system. Also here in Germany, we do exactly the same. You know from the beginning how much hour you need for your course, and at the end you know exactly how much hour you have to teach. It's up, more or less what's happening in the better university in United States is 60 hours. So of course there is exam. We will try to have 2 semesters. And the exam will be homework and research presentation. The student, we will give to the students some research presentation. They have to prepare and to come and to talk, 30%. Then the middle exam, 30%. There's final exam, 40%, and the whole staff are 100%. The objective is to be aligned with the European credit transfer and accumulation system, what we call OCTS. I want in the future that our university, the virtual university, to be aligned with the either European system and even the American system. It's very simple. They have to see what the students have learned, and they can say, yes, it's very good, it's very great. Then you can be aligned with us. You have your background from PV technology. You don't need to do it again, and that's done. And that's what we would like to have in the future. Then project, we will have a lot of projects, because the most important is the practice. PV technology is the practice, it's not the theory. Theory, yes, to learn a lot, to be very clever in which direction you will work, but the theory. And we have, for example, the solar home. Our objective is to deliver greater efficiency per watt to the customer. So we will study what we call solar home project. This means you say your house, you have a refrigerator, you have this, you have that, and you consume every month some amount of kilowatt hour. So what I need, how much module I need, and how to how to adapt your module to the inverter, to the regulator, how much battery you need, etc. All this you will learn. Then, if you can learn this for your home, why not for a commercial and industry project, a big project? If your house need maybe 100 kilowatt hour per month, let's see, or let's see a project of 100 kilowatt hour, then for megawatt, for gigawatt, you can also do project. Also, one topic which is very important in the field is what we call building integration photovoltaic. This means you sit with the architect, etc., and you make a conception of your building. You see here this animation show you the building before and the building once it's done with integrated photovoltaic inside. So in this exercise, a lot of it's a multidisciplinary team. You have the PV producer, you have the customer, stakeholder, you have architect, you have cost manager, landscape consultant. We had just a talk from before about the community, how to do things. So if you want to have a house with PV technology, you have to discuss with landscape consultant. You cannot make your PV in one place where it's not appropriate for that, etc. So it's very important. So it became really a social problem. It's not just a course of PV technology, but you have to learn how to deal with the bank, financial institution, with the contractor, etc. You have to learn this. Okay, architect, builder, and customer are the core of this exercise, but there are other people. You have to bring money if you don't have money in the beginning, etc. Okay, we will learn how to read the data sheet. That's, for example, for the inverter, yes, and that's for the PV, and how to calculate the annual production, your annual production. We will learn how to calculate it, and how much you will inject into to your home, and how much you will sell, etc., etc. Okay. Of course, our course doesn't just stop in PV technology. We will see, and Professor Benitez will talk about this, how to use PV, also wind, it's possible to use it, but I'm interested in PV, how to use it to produce hydrogen. And that's the electrolyzer. So the technique of electrolyzer, it's also in my course. محلل كهربائي. We have also to discuss how to store. The most interesting way to store hydrogen is in material, what we call the hydrure, and also the material like 2D material, because you can intercalate between two layers in 2D material, what Professor Beans has talked about. Okay. We will also study what we call fuel cell. Fuel cell is a device where you can use oxygen from the air, you can use hydrogen, green hydrogen, what you produce in electrolyzer, and you can produce electricity. And this is very interesting, for example, for a hydrogen car. So there are a lot of research and development here for new membrane, because in this kind of device here, the fuel cell, you need a membrane here, which allowed just one kind of proton to go through. And we have to discuss new membrane, new catalyst. You know, if you want to have effectively production of green hydrogen, you need catalyst, because the reaction is very complicated. Even if it seems not, but it's very complicated. You need 4 electrons to split water, 4 electrons. And to do this kind of reaction with a very fast kinetic, you need catalyst, otherwise it's expensive. Okay. So I will a little bit go very fast, because other colleague will give their talk. So we will study a little bit what we call the methanation. This means the green hydrogen with the carbon dioxide from the industry can combine in a reactor here to give you methane, what we call methanation. We will discuss a little bit about the pipeline. And we will also discuss what we call Haber-Bosch process, where you can use nitrogen, hydrogen, green hydrogen, to produce ammoniac. And you know, ammoniac is very important as fertilizer. تصنيع الأسمدة. Okay. So a very, very important program where you can learn not only physics, but also some aspects of chemistry to understand different way of fixing carbon dioxide, how to produce hydrogen. As I told you, you need 4 electrons for that. I make it here. And this kind of cell here, you will have one talk tomorrow from my colleague Thomas Hannabel from Germany. He will give you a talk, and he give you a lot of details. So I don't need to talk too much about it. So there is for the reduction of CO2 or for the production of hydrogen, you need at least this condition. The band gap has to be the right one. The light has to be absorbed. You need catalyst, because you have 4 electron transfer. You have also that your material is well suited for the thermodynamic potential. and the kinetic, because the catalyst, it has to be the best one. So then one of the projects where I worked, my last project in Germany before I moved from the institute, was I developed what we call a roll-to-roll thin film technology. And I had a very nice student from China with whom we worked. And I will talk to you in this, I will develop this kind of project where it's also, we go from the base, the basic physics, to produce material and to make ink, midad, ink formulation. You formulate ink with material, and then this material, this ink, you will deposit it on a roll-to-roll process to fabricate solar cell in a flexible substrate. This is also one of we wrote one very interesting paper on in one journal with I think 30 impact factor of 34, I guess, actually. And I advise you to read this paper and to see what we have done. Okay. I will escape this. Sorry for that, because it's. I think I have to give the time for the floor. So I want to thank you very much. That's one flash about the concept of the virtual learning university, taking as example the photovoltaic PV technology and balance of system. We can do exactly the same for batteries and show you exactly the same presentation, or about other topics. But that's just that you have one idea about where we are, and you are welcome in any time to see our course, our concept. So I am ready with my presentation, and I will give the floor to Dr. Salim.
Thanks a lot, Prof. Ahmed, for giving this information about the VLU. I think we reached to the time for the coming presentation. If there is any questions, it seems that everything is clear. So we can stop now.
Okay.
Wait for the coming session. Thanks a lot. Thank you.
Thank you very much. Thank you very much.